is being recorded.
And as we indicated, this is two parts. Um, and the first part here, there we go. Can you see my slides? Does it look like a full screen kind of thing?
Yep.
This is two parts. The first part, we're going to talk about Pythonization, because this is really, the working group really has kind of divided into two different efforts. One is feeding the other, but is very distinctly different than the other. And the first one is this Pythonization stuff. And if you don't know what I'm talking about, that's okay, because I'm going to tell you. And you do kind of need to know. So this is not just spurious information saying we're doing great work. It's actually stuff that chapter authors and anyone who's going to be editing the text is going to need to know. So just as an example of what we have today. And by today, I mean in MPI 3.1. Oops, sorry. Let me adjust something on my screen here. There we go. Sorry. In point-to-point text, that's TEX, not TXT, sorry, from MPI 3.1, it's amazing, that made it through all the reviewers. Nobody caught that. This is what the LaTeX looks like for the bindings. For the language independent C, one of the Fortrans, no, two of the Fortrans, and the C++. Yes, we have not actually deleted the C++ bindings from the LaTeX, even though they've been deleted. Um, this is what we want to get to. So notice it's a new block. It's begin MPI binding, and that's where the LaTeX ends. Inside that block there is actually Python code. So those are actual function calls, function name, parameter, and so on. I'm going to go through these in a little more detail, so don't worry about the details at the moment. But the idea is that there's basically a little chunk of Python in here that describes each of the MPI bindings, and then that is rendered into LaTeX for you 4 times. Right? So why do we bother? Right? I gave you one reason already, but here's the immediate benefits. And one of them is that you only type the bindings once, right? Versus typing them 4 times, right? Because remember, we have them actually 5 times in MPI 3.1 because C++ is in there, and those are now gone on the 4x branch. But still, 4 times you have to type the bindings, and that's pretty error prone. And we as humans on the forum spend quite a bit of time checking these things and making sure that they are correct and arguing over arcane C and Fortran syntax. So only doing it once is super awesome, if I do say so myself. Just from the perspective of a chapter author, I only have to get it right once, and then it's going to be rendered for me 4 times. And that's the whole point, is that for the most part, everything is just rote transformation into the language independent specification binding, the C binding, the Fortran 90 binding, and the Fortran 08 binding. It is pretty much a one-to-one transformation. So why are we making humans do it? Because humans are terrible and we make errors. So why not have a little bit of code? And the language we chose for that was Python. Now, there's also future stuff that we have talked about and can certainly do. Various people have indicated various levels of interest in these kinds of things. Some people have talked about wanting to be able to programmatically compare different versions of the MPI standard, see when a particular API was introduced or when an API was changed or whatever. You can make global changes to the rendering style. I can't emphasize how important this one is. So just the style of how we render all 4 of those bindings, we could tweak a little Python and instantly change, how it looks for all 400 plus APIs. This is actually the underlying reason why we are doing this in the Big Count working group, because we do want to change that. We want to change, ints to MPI count for a variety of things. Dan will cover that in a little bit. But we don't want to go through and hand edit every single binding potentially multiple times. Because remember, the working group has come forth with like 3 or 4 different proposals about how we do big count. And to date, they have all been significantly modified. So if we had done it the old way of hand editing all the LaTeX, we would have had to go hand edit 400 plus functions 5, 6 times every time the forum changes its mind. Here, now that we just annotate everything semantically, we just change the rendering engine, which is at most a couple hundred lines of Python, and boom, we're doing the whole document. It's beautiful. Third one, and some of the tools people have gotten fairly excited about this, is to generate machine parsable listings of all the MPI routines and their parameters. That can be quite useful. And then you take a half step away from that, and we can actually generate reference C, Fortran 90, and Fortran 8 listing of all the routines. This is not entirely all of MPI.h, but it's a good chunk of it, for example. And so that could be quite useful to make sure that you have the right bindings. I can say specifically that over the past 10 years, we found a handful of errors in the OpenMPI Fortran 90 and Fortran 08 bindings. And you only find that when a user finds out that it's wrong. If we actually have a reference that we can either directly slurp into our implementation or compare against our implementation, that would be fantastic. And you can also do some continuous integration, right? So like you can find out if you accidentally changed a binding or added a binding or deleted a binding or something like that. There are some continuous integration for pull requests possibilities here that are pretty cool. Like I specifically called out in the previous slide, it enables the embigament, right? So the whole idea of big count, do we want to have, you know, two versions of MPI send, one with a small count and one with a large count? That can be more or less transparently done, and I'll talk about this, right? So we can have an MPI send X and an MPI send, or send L, whatever it ends up being called. All right, now, very important to note, this is only for MPI 4 and forward. We are not touching the MPI 3X branch at all. We are extracting data from the 3X branch for comparison, and we'll get to that in a minute, but literally this is only for and forward. We are, even if more errata come out for the 3X branch, none of this stuff is going back there. Now, this is a multi-step process. Like I said, there are two significant activities in the working group. The first one is the Pythonization, and the second one is the embigament. The first one, like I said, we're doing this the first step is to just make the Pythonization part at all and not do the embigament. So it needs to be comparable to 3.1 in almost every way. We're going to talk about the minor differences between 3.1. But for the most part, we just need to Pythonize it with no changes and verify its correctness. And so that's all I am talking about here. Dan is going to talk about the embigament and not so much the Pythonization part of it, but just, you know, what do we, you know, that becomes a regular old ticket, and we actually have good technology to implement that ticket once the Pythonization is done. So let's go back to this simple example here. This is what MPI send looks like after it has been Pythonized. And let's call it out some of the changes here. So just change the indenting a little bit here so you can read things a little bit forward. So a couple things to note about this. There are two mandatory parameters. Okay, sorry. There's two functions here, right? One is function name, and that's just what function are we talking about? It's case sensitive. We're not going to automatically fix case for you or anything like that. So you do MPI capital send, you know, little end. And then you call parameter to describe each parameter in that function. And of course, ordering matters. So, you know, the Python will maintain the order in which you called parameters, so buff count, data type, et cetera, et cetera. There are two mandatory parameters to every call to the parameter function. And yes, I know it's parameter and the parameter function name, and it's a little confusing, but you're all adults, you'll cope. The first one is the name of the parameter itself, pretty self-explanatory. The second one is what we call the kind. And we specifically did not call it a type because this has to apply to both C and two different flavors of Fortran, and potentially someday other languages as well. But you can see in you know, the simple example right here, buff is of type buffer, right? And count I'll talk a little bit more about count, but this is kind of a setup for the embigament of poly exfer number of elements, right? And poly because it may change. There might be more than one. And just a note here, there is a very lengthy list of MPI parameter kinds. This list is still evolving, and I'll send around these slides, and this is actually a link to the full reference guide. We wrote out a wiki instructions for chapter authors, including all the things that you can pass in this parameter function to include a full list of all the types. Now, the embigament stuff, we'll get in a little more detail here, but like this poly x for num element, that's kind of, we're teeing up for the embigament there, because this might generate, two different flavors of the MPI send binding. Now, most functions also have a desc, which is just short for description. And that's the thing that appears in the language independent specifications. That off to the right, you see like, oh, that's the initial address of the sender. Oh, the number of elements in the sender, et cetera, et cetera, et cetera. And then you notice that even one of these guys here, the buffer, has constant equals true, because in the C binding, we pass const for the buffer, right? Now, notice the last one too, communicator does not have a desc. If you don't supply a desc, it'll just use the name of the type in there. So more specifically, it'll look like this. This is actually how MPI send renders after it has been Pythonized. So for example, look at the com there in the language independent specification. You see, oh, it's just communicator because I didn't specify a name, right? And all the other desk labels you see there. Now, there are a couple of new things here. Oops, sorry. That we'll talk about here in a second. But in general, this is the canonical MPI function, MPI send. You start with this, and you get to this. Pretty much the same as what it was in 3.1. All right. Now, here's a more detailed example, because that was a simple one. Let's talk a little more detail. Let's look at MPI type indexed. So same general framework we're talking about here, begin and end MPI binding, and that's the LaTeX part of it. And then inside of that is Python. So for function name, we call MPI type indexed. And then check out the differences in what we see here, right? So I have the count, and that's an array length. And again, we're not going to go into all the types that are available, but array length is one of them. Now, the things that are in red are what are kind of new compared to the simple example. So for example, there's a Python plus to add strings together, because my description of the count parameter was long. It spanned 2 lines. I could have made it just, keep going, but I chose to break it over 2 lines and just use the plus to add 2 strings together, because that's completely valid to do in Python. Cool. Couple more parameters to the parameter function. Array of block lengths is actually an array, right? And so we actually tell the Python here, how long is that array? Well, it's of length count, and count is a different parameter, right? It's also constant because it's an in parameter, and it, when we render it in C, it's const int blah, 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 right? We can also put comments in here, right? So you can put sometimes, just like in LaTeX or any other language, it's useful to put comments. And so you can. That can be useful. And there you see another length equals count and constant equals true, because array of displacements is similar to array of block lengths in that respect. And then notice that we actually have an out variable here too, the last one, new type. So that's the only one you actually have to specify as out. Direction defaults to in, because the vast majority of parameters in MPI bindings are in. So that's a lovely thing that Python allows you to do, is set a default for a value. So if it's not specified, there you go. But here it is an out, so we have to say that it's an out. And you have to say if it's in out as well. Right. Another fun thing, notice that you don't need to escape underscores, right? In LaTeX, you need to escape those, right? That would be array /_of /_blah, right? In the Python, you don't do that. We will take care of that for you, meaning that when we render this to LaTeX, we will take care of the escaping of underscores for you. So it's one little less thing you have to think about, but if you're conditioned by years and years of LaTeX, it's one thing you have to train your brain not to do anymore. You're like, oh, I'm typing some latex, so I need to escape the under. Nope, you don't here because you're actually in a Python block, and we'll take care of that for you. Now, you still do use LaTeX where relevant. So like this descriptions, these in both of these here, we do /mpi arg because that's a LaTeX macro that is part of the description of the count and the array of displacements parameters. So it is totally possible to do that. And then it get a little brain twisting here, I admit, because you're doing LaTeX of MPI arg, but you don't have to escape the underscores. But I will tell you, after my first 200 bindings or so, it became actually fairly pleasing to not have to escape the underscores. So your brain gets used to it pretty quick. Now, here's how it renders here, and it pretty much renders exactly as you expect. Notice a couple of consts in there in the C binding, and you can see up in the language independent bindings, the different fonts. I'm sorry, it didn't really blow up all that well, so it looks a little pixelated because this is a slide and it's not PDF, but it's a normal PDF. It looks pretty much exactly as you would expect. All right, so now let's talk about what the differences are. So again, the whole point in this first bit of the Pythonizing is to make something that is comparable to MPI 3.1. But by definition, it's gonna be not exactly the same. And there's a couple things that are different. Number one, obviously, we've added some new bindings that are in 4.0 that are not in 3.1. So that's an obvious, but let's make sure we mention that. Second, there have been a whole bunch of editorial changes made by Bill and also other Ticket Zero changes that have been made over time. Remember, this is the 4.0x branch, so it's just by definition not the same thing as 3.1. Now we have a bunch of hopefully not contentious changes as well. So we added these little subheadings for each binding, C, F08, and F binding. We went back and forth on whether to call that F90 or F binding. We just left it as F. Honestly, we can do, it's a beauty contest. Whatever the forum wants, we change like one line of code and it updates everywhere. So whatever is desired there. So that's trivial. Second trivial thing is that the humans who wrote MPI LaTeX up to version 3.1 were not entirely consistent. Sometimes in the C bindings, the star for a pointer is on the left, sometimes it's on the right. And sometimes the listing order and the grouping of Fortran parameters is weird. I don't really have any better way to say that. That sometimes, some human in their brain picked an algorithm to list the Fortran parameters this way, and sometimes a different human picked a different way to list them. And so we cannot possibly match that because it's just not consistent throughout the document. And so our engine for rendering does it one particular way. And in most cases, it is the same, but there are certain places where it's not, and I'll show you some. Also, the indenting of the second line of a group of Fortran parameters is non-existent at the moment. Bill is working on the LaTeX magic for that. Yeah, nobody cares. That's just deep, deep LaTeX voodoo that I don't even care about. Bill is going to fix it for us. But it is something that you'll notice different between 3.1 and this. And then also, just because sometimes the spacing is different, hyphenization at end of lines sometimes is different. So let's have a look at some of these differences, right? So the binding subheadings, you probably already noticed it in the examples that I showed already. So on the left is a snapshot from MPI 3.1. And again, these are all screenshots of PDFs, so they look a little pixelated, but it's just because I had to turn them into pings to put them here in the slides. On the right, you see we have these little headings. And these were, I think this came out of a forum meeting. I'm not sure which one. These were decided on because we're assuming that the embiggening is going to have multiple bindings on each language. And it's just kind of helpful to look at and have a visual barrier between the different languages. That's the only reason that they are there. The star placement. So again, you can even see this in MPI send. So in MPI 3.1, the star is on the left, and in ours, the star is on the right. We pseudo arbitrarily picked the right because, like I said, it's just not consistent throughout MPI 3.1. So it's a coin flip. Which way do you want to go? Here's the parameter listing ordering thing. Now, I am not talking about the order of parameters in the actual API listing itself. So MPI test any, once you start the parentheses, obviously the order of those matter. And of course, those will match. What I'm talking about is the listing of parameters that follows that, where the order actually does not matter. It does not change the semantic meaning to the Fortran compiler at all, no matter what order those parameters are listed. So on the left in 3.1, we have logical flag comes first and then all the integers. And our rendering, the integers come first and logical flag comes second. Again, to the compiler, these are identical, and it does not matter at all. Now, here's some things where things might get a little contentious, and this is in particular what we want to get some feedback on. So the description to the right in the language independent specifications is sometimes different in ours versus what is in 3.1. And for the most part, it's because 3.1 is not consistent because it was written by humans and it was a huge document and things changed over time, etc. So particularly the treatment of different types of integers. So whether it says non-negative or positive or state or plain or not even listed at all. Let me just show you some of these. So for example, MPI send, the destination is listed as an integer. But technically a rank is a non-negative integer. And so our engine renders this as a non-negative integer. And that's because in other places in the standard, it talks about ranks as non-negative integers, and the parenthetical to the right of the language independent specification says non-negative integer, right? And so we get to this point of like, all right, well, in some places do we say integer, and in other places do we say non-negative integer? No, our conclusion was we should describe ranks the same way all the way through. And so let's put non-negative integer everywhere where a rank is intended. So technically, this is a clarification beyond what MPI 3.1 says, but it is correct. And the only way you could get a non-negative integer is if you pass proc null, but that value is never specified and therefore is implementation independent. I'm sorry, implementation dependent. And so if a negative value is passed, that is not visible to the user. So saying non-negative integer there is okay, even if your implementation's value of MPI proc null is -1. So there's one example. Here's another example. Group translate ranks. And yes, it really, we had to examine all of these even obscure functions. In MPI 3.1, they didn't put a parenthetical describing what those ranks 1 and ranks 2 are. And ours, we did, because they are an array of non-negative integers, because they're ranks. And so, again, technically, this is a clarification above MPI 3.1, but it is correct. Here's an example 3. So status set elements as a count here, and the number of blah, blah, blah. MPI 3.1 calls it an integer, and we call it a non-negative integer because in this case, you can't, because this is the same count that was passed through MPI send and MPI receive and so on. And over there, it is described as a non-negative integer, right? This is a case where humans were not consistent. In one place, we said non-negative integer, but in another place, we said integer, but we're talking about the exact same value. And so again, this is a clarification above MPI 3.1, but it is correct. Then we have cases where it's not clear what the right thing is to do. So for example, the two functions on the left here in MPI 3.1, group compare and topo test. The out variable is actually an enum value, right? So in group compare, you get whether they're similar, identical, whatever. I don't remember all the values. And in topo test, you find out whether it's a graph or a Cartesian or neither or whatever. In topo test, they call it a state, and in group compare, they call it an integer. What should we call this in the Pythonization one? I'd actually kind of like to call it a state, but I don't have a huge opinion here. And if no one cares, we'll pick something and do it. But again, this is a difference. No matter what we do on the Pythonization side, we will disagree with something. I'm sorry, we will not disagree with, but we will disagree with the rendering in MPI 3.1, even though it's a clarification and still correct. With all of this, we all know how big MPI is. How do we check this for correctness? Because great, humans go through, we change all this to Pythonization. How do we make sure that we got that actually correct? So we're doing some machine-assisted comparison to MPI 3.1 and human-assisted comparison to 3.1. So we are working on an automated comparison of the binding, extracting the LaTeX from the 3.1 branch and comparing it to the generated LaTeX from the 4.0x branch. And anything that's not the same, just throw it in a file and let a human review it. And believe it or not, there are fewer cases of this than you would think. And so it's really helpful to not only get human eyes on it and just check it, rote, like have each of the chapter authors go along and say, yep, this is good, this is good, this is good. But then also have this additional tool that says, okay, here's, 5 places in your chapter where things were different. Go look at that. I'm not even going to try and tell you which one is right. I just noticed that they're different. We're not trying to make this tool be too clever. And human, go figure it out and see if that is correct, if that falls in the realm of someone made an error or this is a clarification above 3.1. Someone just needs to go look at this and determine whether it's okay or not. So here's our current status. Nearly all the chapters of the 3.1 quote unquote conversion is complete. Remember, this is only on the 4 branch, but just the Pythonization to make it comparable to 3.1. That's why I called it that. That's nearly done. I would say, I don't know, let me take a swag at it and say 3/4 of the doc is done. And we're working off in a branch. It's been a ton of work and has required a ton of time, but this is really good and useful stuff. Pretty soon, we're going to be ready to submit this to chapter authors and committees for correctness. And we're going to ask people to check the rendered PDFs version, versus 3.1. And we'll also give you a list of, here's the things that we found in our automated correctness checker, 3.1 versus 4.0 as well. What's the end state for this? Well, it's not exactly a ticket 0. It's not exactly a full-on ticket either, because I mean, hypothetically, there's no semantic differences compared to 3.1. So there's really nothing to vote on because we vote on text, and hypothetically, the text is more or less the same. That being said, as I just showed you in the slides, there are clarifications. And we can decide whether we want to vote on this or just merge it. I'm kind of assuming that, we want people outside the working group to get eyes on this and make sure that we're not crazy and so on, and make sure that everybody's going to be good with this. Here is a link to the ticket that we have for all the Pythonization stuff. And right now there's about 6,000 commits on there. We're going to squash it all down before we're done, but we're working in a rapid kind of fashion, like, I did 5 more bindings, commit, push, right? And just push it on the ticket. It'll all be squashed down before it's done. Now, the next part, though, is assuming the forum signs off on all of this, then this becomes our reality, right? And all of you have to start writing bindings in the new way and editing bindings that have been converted over. So we actually wrote a wiki with instructions for everybody. And the feedback I got 2 weeks ago was like, hey, what about those of us who don't know Python? I was like, oh, that's actually a really good point. So I put in a whole page about, if you don't know Python, these are probably the 5 things you need to know. We're not actually using super deep Python. We're not using a whole lot of Python at all, honestly, but you do need to know a few things about string handling and indenting and blah, 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 a couple minor things. You don't have to become a Python expert, but there are a few things you need to know. That's it. I'm actually shocked that nobody interrupted me with a question. Does anybody have any questions? All right, I'm going to show you the wiki here. Can you all still see the wiki, like my web browser?
Yep.
Okay, cool. So here it is right here. If you look at the simple example, that's just the MPI send that we looked at a second ago. And I'm like, oh, here's what it looks like with a little bit of LaTeX above it. And see, there's even a LaTeX before that and whatnot. And then here's what it renders to. Lovely. Um, and then if you don't know Python, here's a few things you need to know. If you do know Python, there's really nothing you can skip this whole thing. But for those of you who don't know Python, here's the 6 things you need to know. Python indenting, string handling, line breaks. This is the underscore escaping, how you do comments, and Boolean values, right? So helpful stuff here, hopefully easily digestible. And then I have one big example here at the end to kind of tie it all together if you want to.
So Jeff, I assume you're going to move these wiki pages over to the main forum wiki once everything's done.
Yeah, that's a good. Uh, Timing TBD, but yes, this will need to move over to the main one. Good point. Thank you, Wesley.
And it would probably make sense to put it on the standard wiki, not
Yeah,
the
yeah.
BSG wiki.
So let's see this one. Yeah, this is a public wiki right now, but you're right. It needs to go on the public wiki on the main forum
I mean, it
side.
doesn't. There's nothing we don't want to be public here. It's just that nobody cares about this. That isn't already editing the doc.
Yeah, but when you go, you're like trying to finish your stupid new function, and it's like T minus 2.1 right before the forum meeting. You're like, how do I do this Python thing? You need to know where to find it. So, um, yeah, good point. Thank you, Wesley. What else we got? General guidelines. Couple of points here. Like we are actually deleting the old LaTeX bindings. Please God, don't comment them out. No, we're actually deleting them. Let's be 100% clear. The goal is to delete the old bindings. Do not just comment them out. Then a couple things like when you do this, you're still just invoking make and the right magic of rendering to LaTeX and then rendering the LaTeX to PDF. That just happens for you behind the scenes. From that perspective, there's nothing new that you need to do. You will need Python 3 though. I should put that in here. You will need Python 3. Python 2 is going end of life by the end of this year anyway, so stop using Python 2. What else we got? Rationale for here's why we're doing this. Um, Lovely thing, just a couple quick points. And then here is the important one, the detailed reference guide. For the most part, you can look at this simple example and get 90% of what you need to do. Like, oh, function name, oh, parameter, and so on, right? Like, oh, here's a bunch of different types and stuff like that. Just call parameter a bunch of times. Look at all the other examples in the LaTeX. You're probably just going to be copying, pasting from some other one anyway. There you go. However, there is a complete reference guide for all the functions that we have. So like function name and parameter are the 2 big ones that you're going to call. And parameter, here's all the different kinds that we take and what they are, right? And this is still evolving over time. That being said, there are a handful, go all the way down here to the bottom. There we go. There's a handful of other functions. So like MPI init, for example, has some arguments that don't show up in the Fortran side. MPI wtick and wtime have a different return type. MPI wtick and wtime also don't have an iError parameter. This one we may need for embigament. We'll get back to that one. Couple of functions like MPI size of, there's no C binding, right? So there's like just additional directives you sometimes need to give to the rendering engine so that it does the right things. And so a handful of functions like this. Yeah, that's it. But 95% of what you need to do is just function name and parameter. And that's it. So the simple example is there and the detailed reference guide is there. Between that, you should be able to find, oh, and the 400 plus other examples that you'll find in the rest of the LaTeX, you should be able to figure out what you need to do. Other than that, that's the end of the Pythonizing. questions? This is shocking. This has got to be the first MPI presentation ever where there were no questions.
Too much inside baseball. People don't handle it.
That's true. But it's going to affect all of you, so don't say you didn't know.
So I do support bringing this as at least an errata or something that the forum can raise their hands and say, yeah, that sounds good, at least once.
Yeah. And that'll probably be December.
Oh yeah, I guess you have an extra 3 months if it's only an errata.
Yeah. Okay. Well, with that, I'm going to turn it over to Dan.
So I should try and share my where's Google Chrome? That one. Okay, now what do?
The big present button in the top right.
Top right, that'd be under your picture then.
No, to the right of my, yeah, right. Oh, right.
It's all right, I moved you. Okay, so hopefully you can see the title slide.
Scared
Yes.
already.
Sorry?
I'm scared already. That is
Excellent.
a terrifying
Good.
title slide. So
Yeah, yeah. Hopefully we're going to take the wheel spin route round the scary thing rather than down the drain. Okay, so this is about embiggening, as in 64-bit, compliant or whatever you want to call it, big count, excess count, something, making MPI accept bigger numbers than can be put into an integer type. So yeah, this is the week before SC. We don't have a huge update. We do have some things to say here. So there's a picture of a nice sunset to put you in the right frame of mind. So yeah, basically we're gonna talk about the current status of where we've got to with the large count stuff, big count stuff, extra count stuff, whatever you want to call it. We have made some decisions. I think we've now resolved all of the really big issues. So I think it's just now turning the handle. Mostly it's modifying the Python so that it renders correctly, and that's picking the right kinds when you're setting up the parameters. It's picking up the right kind so that the right thing happens. So really, these slides are then going to be talking about the decisions that. Hold on a
Just
second.
to clarify, Dan, too, there is going to be some supporting text about this as well.
Yeah, I guess so. One of my colleagues has just stepped in. If you just give me a moment or two, if I can just find a way of muting this thing. Sorry for the interruption.
You have to go to the WebEx little bar at the top.
All right. Okay. Yeah, I see. Hold on. What am I? Where's the mute button of this thing? There.
Well, you get a sneak peek at the terminology slide. So I can talk about this till Dan comes back. Through this process, we found out that there is actually not a very good understanding of a bunch of terms that are used all throughout MPI, meaning we thought we understood them, just like the forum thought they understood them. And then we found out we really did not understand them as they are very precisely defined. And for example, what exactly is an MPI AINT? We had... there was a big brouhaha over that, and that affects what we are talking about here. So, yeah, this is very important. So, Dan, let me know when you're back. There are several terms that are important to embiggerment that are listed here on the left, and they actually are defined in the MPI specification. That might be Dan going off mute. Are you back, Dan?
Yes. Sorry about that. One of my colleagues had a question about the exam paper that really needs to be dealt with right now, but fine. Where's this present button? So I guess you said something, Jeff.
We found there's a bunch of terms that everybody thinks they know what they mean, but we at least found out that we didn't know what they mean. So we thought we'd start with that right here.
Yeah, so I think this is that's a good segue into this. So yeah, this is a list of things that we do use these terms both outside of the MPI standard and actually in the document itself, and they have particular meanings. And I think this has forced us to combine and merge our collective understanding of what these things are. So some people understood some of these better than others, and we've had various side meetings and working group meetings and so on to try and get to a collective understanding of what these terms actually mean, and how they're different in particular. So even if they are currently rendered as the same type in the document, which they are for basically most of these, then we actually do need to know what the differences are, because we're going to treat them differently when we embiggen them. So yeah, I guess there's a section reference here, so you can actually read about what MPI says in terms of defining these things. And so the first one here, the section is actually about array arguments. I think it's called array arguments, and then it says that that it's actually talking about the length of an array argument. And so we've called that a length. The term that we want to define is length. What we mean by that, and what the section referenced is meaning, is it's a parameter that tells MPI how many elements there are in some other parameter, which is an array argument. In C, you don't know how long a parameter is, how long an array is, so you need a second parameter which tells you how many elements you're actually using in the array parameter. That's what we mean. Right? And it's always going to be a non-negative integer. So for count, there's a different section, and this is the MPI definition of the MPI count type in MPI. So it's often the number of data types in a buffer or in a data type or in some other scenario. It's not always used like that. There are other situations where we use MPI count, but that gives you a flavor for what this thing's used for. It's a non-negative integer in almost all of the cases. We can't think of one where it's actually you supply a signed value, but it is a signed type, and so potentially it could hold a signed value. And then we've got displacements is the difference between two absolute memory addresses. That's always a number, and it's stored in an MPI aint type. Absolute addresses are also stored in MPI aint type, but they are a bit pattern that represents a location in memory, and it's probably not a number. It might be, but you can't guarantee what that bit pattern is or what format that bit pattern is in. So that's an interesting thing, which we'll come back to in future slides. So if you're trying to use one of these things, you have to be aware that it has this dual nature. Then there's also an offset, file offset. So that's a position in a file. It's a signed integer. This is typically represented by MPI offset, and that's got a different section in MPI to describe it. And then something else that's useful, it's not a type or a kind per se, but this is a useful definition that is buried somewhere in the middle of section 4 of chapter 4. There is a definition of sequential storage in MPI, which is derived from the definition of sequential storage in the C language, and I think there's a similar thing in Fortran as well. Basically, in MPI, displacements are only really valid within sequential storage, and sequential storage means the memory that backs up variables that are in the same array or the same structure in C, or the same common block in Fortran. So these are language definitions which we've sort of unioned together and then co-opted to define our thing that we call sequential storage. So those are terms that you need to know what those are in order to be able to understand when we say that we're making counts bigger, that we're not making lengths bigger. What's the difference? Well, this is the difference between these terms. Okay. So the first one, length parameters. We are not going to embiggen length parameters. This is a general decision across the whole document. So we have to call out, now that we've got the definitions, length is not the same thing as count. We are not going to change this. So an example of this is the count that's in the wait all function. How many requests are we going to give to the wait all function, or the wait sum function, or the wait any function, or the test all test, all of these functions. When it's used in that sort of sense, even though it's called a count parameter, the name of the parameter is count. It's not a count parameter. This is a length. This is doing the job of describing the length of another parameter, and that's the only job it's doing. And so in that situation, we're not going to change it because it really doesn't make sense to, or at least to us, in particular the wait all function, it doesn't really make sense to give more than 32 bits worth, of requests to the wait all function. If you're doing that, then you've got a problem that is not to do with big count. So that's the first decision. We aren't going to do lengths. Okay. The second decision is we are going to do all of the count parameters. So this is the one that's, X count, big count, large count. This is the one that makes a huge amount of sense. This is the obvious one. Of course, big count is going to make all the counts bigger. So we are going to embiggen all of the count parameters, the ones that are really doing the count job, to MPI count. Some of them already are. Some of them are int currently. Where they are int, we will have a new function which has the same parameters, but where the count parameter, or count parameters plural if there's more than one, will be MPI count type, like this example here. So I've given the C functions here. There is an MPI send function. In MPI 4.0 there will be a send L function as well, L for large. So that's just what we're doing. So the original send function will still exist, and it will be unchanged, at least by us, in 4.0. But there will be this additional function. So in C there will be additional functions because we went down the route of trying to do generics and polymorphism, and that's a rat hole that we didn't find anything useful.
The phrase you're looking for is that it failed spectacularly.
Yeah, that's another phrase. That's another way of phrasing the same thing. Yes. So polymorphism in C is not useful. It's not easy to use. It doesn't do the job we want it to do. We're not using it. So we would have to define these functions anyway. And so there's a whole bunch of reasons. We went through them. This is the solution we came up with. There is just going to be a whole bunch more functions, and they're going to have _L on the end. And that's the best solution we've come up with so far after many tries of different things. So in Fortran, Fortran does polymorphism a lot better. So there will be an _L specific procedure name, but the user isn't going to see it because it's going to be Fortran does its polymorphism thing, and it will just look like polymorphism to the user. Although tools will see that there is an _L specific procedure name in exactly the same way as this, barring case and Fortran language differences. So a couple of other examples here, things like the block length and stride length in data type creation functions. Those are describing a count, a number of data types, or a number of units of the data type. Those are doing the same job conceptually, semantically as this count in the send function here. Those are counts by our definition, not lengths or any of the other things. So those are going to get made into MPI count parameters as well, with the same sort of thing, with an _L version of the function. So that's 2. Then the next one we're going to look at here is offset. That's not the same order as the table, but offset comes next because it's an easier decision. There are two places where offset is used as a term. In the RMA functions, a lot of the parameters are called things like target disp, so it's a displacement. But the text also refers to that as an offset within a window. There are some terminology things, so we're lumping that in with offset here. But the short version of this is we're not going to change that, right? This is already aint, and it needs to be aint because that's the type that refers to to memory displacements and locations and so on, it shouldn't be an MPI count, because that is potentially a bigger type in terms of number of bits of storage that it uses, and all of the hardware optimizations that care about this need it to be an AINT type, not a count type. If the count type is too many bits, it would change the wire protocol. It would, no, this is terrible. We shouldn't change this. It doesn't need to be changed because MPI AINT is big enough to store any displacement in memory, any location in memory, and that's its definition. So, and all of the RMA stuff is doing operations on memory, and so there's no reason to make this bigger. There is no situation where you would need a type that was bigger than this. So that's an easy decision. We can just leave all of that part of the RMA chapter, just leave it alone. The same thing goes for in the IO chapter. Everywhere where it matters, the IO chapter uses a type called MPI offset already, which is already big enough and defined to be big enough to do whatever you want to do with files. And so we don't need to do anything. There's no work for us to do in that chapter either. So that's offsets. Okay, so the next one is maybe one of the most contentious ones, displacements and addresses. So these are going to be made bigger. There's currently a lot of situations where displacements, real displacement in memory, so a displacement in bytes, a difference between two absolute addresses, that sort of displacement, or an absolute address, both of those are used, and they are currently typed in the API as int, which actually doesn't cover either of those two cases. Right? It's not big enough to hold necessarily a displacement in memory if memory is bigger than the how many gigabytes. Right? If I have 16 gigabytes of local memory, I can't actually describe every displacement that's possible in that memory, and also I can't necessarily store every memory location, because I'm not using MPI AINT, which is the thing that stores the bit pattern that represents a location in memory. So actually things like all-to-all W with its int displacements doesn't serve our purposes for either of these two use cases. So this is really important that we do this. We only need to make it up to the AINT size type, not the MPI count, because they only ever send and communicate data that's in memory, and so these are definitely memory displacements, memory addresses, and so AINT is big enough and exactly the right type to use. It also has the polymorphic behavior that we need, which I'll get to on the next slide. So another example is in the data types chapter. So some of this work has already been done a long time ago, when the data type stuff was first being put in, and well before we started changing stuff. So in 3x, for example, there is an MPI type indexed. This creates a type, and you give it an array of displacements, which is typed as int. And there is also an MPI type create h indexed, which is I don't know what the h is for, hardware, I guess. But this one is exactly the same, does exactly the same job, except that the array of displacements is provided as an array of AINTs, MPI AINTs, instead of just an array of ints. So the embiggerment to cope with memory addresses and memory displacements has already been done. There is a separate function already in MPI, which has a completely different name with h indexed. So part of our job is already done. So in discussing this inside and outside the working group, there is also, data types are also used to address files. They're used with files. Files can be bigger than memory, and so AINT, certainly int isn't big enough to describe every displacement you could have in a file, every offset you could have in a file. But actually MPI AINT isn't either. What we need is MPI offset, or something at least as big as offset. So what we're going to do there, the work that we are going to do here is add a type indexed that has an MPI count array. So this one at the bottom here of the slide, we're going to do an MPI type indexed with an underscore L on the end. So this is the bigger version of the one that just had integers. MPI count is a bigger type of integer, and so that's why it's underscore L on the indexed version and not H indexed L, because there isn't a bigger type than MPI aint that does the same job, right? MPI count doesn't do the same job, it does a different job. So that sort of explains the displacements and addresses. It does leave a couple of obvious questions, and so there is just one more thing about that. So during this sort of discussion of types and these various terms that we use, and what is this, what's a length, what's a count, what's a displacement, and so on, MPI aint was discussed at great length, no pun intended, and we came up with well, we as the working group had misunderstood what MPI aint was as a type, what it was capable of doing, and we've now discovered a whole bunch of references in the standard, which are in the table at the beginning. The upshot being that MPI aint is a polymorphic type, which some people obviously knew and some people didn't. So in a call with Rolf and Jeff Hammond and Jim Dinan, we sort of came up with, it's the nearest thing that we can come up with is that it should be something like this union on the right hand side here. That's not actually right, but it's a sort of it's a good stab in the right sort of general direction as to how this type is actually defined or used, or the way it's defined by MPI. It is effectively a union type. For those that are C programmers and know what a union type is, it can certainly store an absolute address or a displacement between two absolute addresses, or the size of a chunk of sequential storage. Possibly there are uses where you might it might be able to store a pointer or an offset. We're not really sure about those, but it already doesn't matter because you've got at least 3 use cases that are different to each other. And in C, if you were to try and use the canonical C types, you'd be using a different type. You'd be using in pointer T or pointer diff T or size T, or there's a bunch of different types for these different uses in languages, but MPI uses the same thing. It uses MPI aint for these things. So if you were trying to use this, you can, if you had an MPI aint, conceptually at least, you could access the address field of your union, and it would give you a bit pattern that represented an actual address, a location in memory. You have no idea what the format of that bit string is. You can't do any operations on it and rely on those operations because you don't know what format the bit string is in. But you could potentially access that address. You could copy it to somewhere else. But you can't access, if you stored an address into this aint, you can't then access it like a displacement or a size, because those things interpret the bit pattern it finds as an integer, as a number, and that's not what's stored there. And so this causes all sorts of trouble. But we've now come to this realization. This is the way MPI has defined MPI aint. And so that changes our decisions about what to make these new big types. Where we see int in the 3.1 standard, what should we make it in the 4.0 standard for the bigger version of that? In some cases, we make int an MPI aint because that's what it should have been in the first place. Sometimes we make it MPI count because it's doing the job of just counting something. And we now know better when and how to make that decision. So the key point here is that some of these things are not numbers, and so the only way to manipulate those things is using the MPI aint diff and MPI aint add functions that were added to MPI specifically for manipulating the things that aren't numbers in MPI aint. types. So that's sort of a rationale for our decisions around displacements and addresses. Some more information about that is that even when you think that the function is only going to have a displacement usage, there are situations where you can actually supply addresses to that function. So, for example, if you create a data type, you don't know what the base address is that's going to be used with that data type, and so MPI doesn't actually know whether the displacements that you've given, or the AINT values that you've given, whether they are displacements or absolute addresses. It doesn't know that until you actually do, for example, send using that data type, and then your buffer address tells MPI how to interpret the stuff that was given to the data type when it was created. This seems interesting to implement, but this is the way it is. If you supply MPI bottom to MPI send, then your data types become something that involves absolute addresses, and if you give an actual variable, the address of an actual variable, then all of the data type AINTs become displacements at that point, and so you have to create the data type in the right way to use it in those two different ways. This is just deeper understanding of how MPI has been put together. So hopefully that gives you some information about what we've done, what we are doing, and some reasoning behind why it's going to look the way it's going to look. So yeah, the embiggening is definitely happening. We are, as a working group, a long way through doing the work for this. We are working to the deadline of getting it ready for December. So hopefully we'll be able to read this, and if you've got questions, now would be a good time to ask them rather than in December, because we're more likely to be able to react before it's too late. So questions?
This is staggering.
Yeah.
Presentations with no questions.
Yeah.
If you want somebody to be ice, the void star probably shouldn't be there in your union.
Yeah. So
Maybe there.
Well, it's covered by the int pointer t, right? It's an integer, not a pointer type.
Okay.
yeah. So I picked that up, Jim, from our conversation. Jeff Hammond had put that in the union that he put into the chat window that as we were talking. And it was a late addition during the conversation, and I didn't really pick up why that was added, but I faithfully, copied it across because I didn't really, I understood
Just
the other
wrong.
three.
It's
Yeah, I understood
the
the other
first time.
three absolutely, but I didn't really pick up where the pointer thing had come from in terms of, is there an example where we give a pointer to it? I don't think there is, but I didn't want to just sort of get rid of it without some sort of.
Yeah, I mean the tricky thing is that it's something much worse than a union type, because it's basically just a bare integer type that you can stick different things into. So
Yeah, this is
you
the
kind
thing,
of lose all of the nice successor things that you would have had if it were a union type.
Yeah, this is the thing. It's yeah, you're right. It's worse than a union. It is as though the MPI library writers had created a union type and then wrapped an opaque type around it and given it to the user as here's a place to dump some bits.
Well, yeah, I mean, to sort of defend their honor, I mean, because of language interoperability, that just wasn't really an option, I think, back in the day.
Yeah, that's true. Yeah, this has got to work in Fortran as well. And is there a union type in Fortran? I don't actually know Fortran well enough to know the answer. Even now, is there such a thing? Is there a better way of doing it? Well, there's status is a structure in C, and anyway, I don't know. Maybe there's a better way of implementing this. This working group really isn't trying to change the definition of anything. It's trying to just pick the right type from the ones that we've already got. We're not trying to define new types or modify the semantics of existing types or anything like that. So I'm not trying to. This working group is not trying to redefine MPI AINT here. Maybe that's a good idea. Maybe that's a proposal that should happen at some point. Maybe there's a better way of presenting this to the user now, a different API that would be.
No, I think that the outcome, like the concern that we had going into that AINT discussion that we had a few weeks ago, was that there could be, we weren't sure if there were situations where you would need to deal with absolute addresses inside of an MPI count. And we were able to convince ourselves that that's not a problem and not something that we should be worried about. Right?
Yeah.
Because if you do have to deal with absolute addresses, the representation of an absolute address as an integer is implementation defined. And this is true even for the int pointer t-type in C. And so you lose the ability to do language level operations on it just because the representation is not known to you, so you don't know whether it's valid to do those things or not. So we were able to kind of cross that off the list of concerns about MPI count, which is a good thing.
Yeah, so the only type that has this polymorphic behavior is MPI AINT, and we can limit it to that type. If you need the polymorphic behavior, then you need a MPI AINT. But actually, in most cases, all of the other cases, you don't need that polymorphic behavior. You just need a big type, and so you need MPI count or offset or something else. Yeah. Yeah, so that's sort of why in the data types slide, that's why we're creating a new data type creation function, even though we've got one that has int as an input parameter and a different one that has a MPI AINT as an input parameter. We need the third one with MPI count as its input parameter because MPI count doesn't have the polymorphic behavior of MPI AINT, so you need to keep the MPI AINT one. But it's also MPI AINT isn't big enough to deal with the full size of files, which are bigger than memory potentially. And so you need something that's bigger, that can hold bigger numbers than MPI AINT, but you don't need in that situation to have absolute addresses. And so the count one doesn't need to do the polymorphic stuff. You've got the AINT one that does the polymorphic stuff. And so
and maybe just to give an example, for folks who maybe don't have the AINT stuff fresh in their head, is an example of the polymorphism is that in an MPI send operation, you can give a pointer to the source buffer, and you can have a data type that specifies some data that's to be sent relative to that that pointer that's passed as the send buffer pointer. You can also pass MPI bottom as the send buffer pointer, and your data type can be specified in terms of absolute addresses in memory. And so that's kind of where this polymorphic stuff gets a little bit tricky, in that the data type interfaces, you don't really know, until you see that send operation, you don't really know whether the data type contains absolute or relative addresses. The user builds a data type and you find out when the communication operation is performed, which of these ways it should be interpreted.
And the same data type constructed exactly the same way, exactly the same data type can be used in both ways. You could do a send with MPI bottom, and then the next line of code use the same data type in the next send call, which gives the address of an actual send buffer, and that data type can therefore be interpreted. That would be erroneous because you can do it. You can code it up, but it would be erroneous because the MPI AINTs that it was constructed with can't be doing both jobs. They are either absolute addresses or they're displacements, but they can't be both. So you would need to create two different data types, even though it looks like you can get away with just one. That's right, isn't it, Jim? Just to check.
Yeah, a user could do that. It would be erroneous, and I believe the behavior is undefined. Yeah, the user shouldn't do that. But so I mean, the upshot of it is that we don't, so I think and Dan, I mean, you should correct me if I'm wrong here, but the result of our analysis was that we don't have these same sort of concerns with respect to count, and so we were able to kind of, long story short, we were able to kind of cross that off the list of things to be worried about.
Yeah, so I think that the remit of the large count working group has expanded beyond just making the ints that are doing a count job into MPI counts. It's also now covering converting ints that are doing a displacement job into MPI A ints and so on. So there were situations where we didn't know whether we should be making something an MPI A int or an MPI count, and now we do know because we can use this this polymorphic behavior to make the decision. If it needs that behavior, then it has to be an MPI A int because that behavior isn't supported by MPI count. It doesn't need to be supported by MPI count. And if you need something bigger than it, then you need the count one. So it's been helpful to do it, but that's why we need to know this in this working group and why we've talked about it here. So any other questions, concerns, issues? Okay, that was incredibly painless.
Was incredibly painless. I sent links for both of these slide decks to the MPI forum list. In particular, the Pythonization one has a couple links for the wiki and the ticket in them, but use them for your reference. All we got.
Yep. So I think we're done.
All right, I'm going to stop the recording.
Okay.